Hello everyone, my name is Filipe da Nóbrega. I am a Brazilian PhD student in France at École Normale de Lyon under the supervision of Etienne Gis, and today I'm really happy for the opportunity to talk to you about my work on osculating conics of a smooth curve on the projective plane. So first I'll begin with a straightforward introduction just to state the main theorem, and then we'll follow the necessary steps in order to prove it. Okay? So first, let's consider osculating circles. There is a classic result called the Tate-Keniza theorem, which states that the osculating circles of a smooth curve on R2 with no inflection point or vertex are disjoint and nested. So just to remind you, the vertex is the critical point of the curvature of the curve, and as long as there's no vertex or inflection point on this arc, the osculating circles are disjoint. That means they do not intersect if you take any two osculating circles, and they are also nested, which means they are one inside of the other. So we have this pretty picture here, which actually gives a foliation of this region of the plane. The theorem we are going to prove today is closely related to the last one, but instead of talking about osculating circles, we're going to talk about osculating conics of a smooth arc. And I chose to talk on the projective plane because really that's the most suitable space to work with conics. And so the theorem states that if this curve has no inflection point nor sextetic point, which is the equivalent to the vertex in this case, then the osculating conics are disjoint and nested, just as in the previous case. And in fact, up to this point, this was already known and proved. I think Hayashi was the first one to prove this. But we can go further because we can show that there's an even stronger condition on their relative position. They're not just disjoint and nested, but they're also more than that. They are convexly nested, which is a term that I will explain the meaning throughout the exposition. So here we have another curve and a couple of osculating conics, in this case ellipses, drawn. And so just to clear the meaning of a sextetic point, another way of talking about a vertex is the point of the curve where the osculating circle has a contact of order higher than supposed, higher than expected, let's say. In general, an osculating circle has a contact of order 3 with the curve at that point. That's all we can hope for in general, but sometimes in particular points, which are called the vertices, the contact is of order even higher, so 4 or above. And a sextetic point is the same for osculating conics. So a osculating conic in general has a contact of order 5 or higher with the curve at the given point, and the sextetic point are those where you have a contact of order 6 or higher, so higher than expected. Okay, so let's start our way to the proof of this theorem. First, we'll talk a little bit about the space of conics. So we know that a conic can be given implicitly by an algebraic equation of this form, which can also be written in a matrix like this. And you can even classify them because since the conics are given as the isotropic set of this matrix, its nature changes with the signature of the matrix. For us in particular, we're interested in this case right here of the conics which are irreducible but also present in the real projective plane. So as I said, we are going to work on the open set omega of the forms of signature 2, 1 or 1, 2, since the oscillating conics of a curve are all of this kind. But actually this is a line bundle of the true space of conics, because if you take a multiple of the same expression, those two different expressions give the same curve. They represent the same conic in the projective plane. So really we should projectivize if we really want to work on the space of conics itself. But as we'll see, it is fruitful to work on this line bundle because it gives us a degree of freedom which we'll exploit a little later. So what we'll do is to construct a map phi which takes two conics, two elements of omega, and produces a polynomial which will classify their relative position, which will give us some information about these conics. Here, what I'm calling F24 is the space of forms on two variables and of degree 4, so binary quartics. This will be our main tool, which we'll use to analyze the position of two conics. It will tell us, for example, if two conics are nested or not, if they are convexly nested or not. depending on the properties of the polynomial that it results. Okay, so to construct this tool, we'll need two ingredients. First of all, an implicit equation, which we already have, and next we need a polynomial parametrization. So what I mean by that, we take any point on a conic and we consider the pencil of lines through it, which is isomorphic to a projective line, RP1, right? And we have a bijection between this RP1 and the conic itself, because each of these lines will intersect the conic in another point. And we can even do this algebraically, we can parametrize. Normally we have x and y described as rational functions, but since we are working on the projective plane, we have the third homogeneous coordinate z, and then we can multiply everything by the quotient, in this case t squared plus w squared, and with that we have a polynomial parametrization of the conic, which we'll call rho. So rho of a conic, u, will be the polynomial parametrization constructed in such a way. Alright, now we can define the map phi. Taking two conics u and v, phi of vu would be this composite right here. We'll take the polynomial parametrization of u and we'll evaluate this in the implicit equation of v. And this will produce a homogeneous polynomial of degree 4 on the two variables t and w. For example, we can consider two conics, the unitary circle, which we already have the polynomial parametrization, and here I chose an ellipse given by this expression. So if we compute phi of vu, it gives us this polynomial, and by studying this polynomial we can talk about the relation of u and v. For example, it has 4 roots, namely a double root at t equals to -1 and 2 simple roots, which are here. They point out exactly at which lines they are the intersections of these two conics. So this is how this tool really works. We take two conics and it gives us a polynomial whose roots correspond, are in bijection with the intersections of the two conics. Okay, so now we should talk about some structure in the space of binary quartics, since these polynomials produced by the function phi tells us the relation of the two conics. So it is important to be able to classify these polynomials with respect to some particular properties. So here's a definition. A subset B of this space of forms, here is in general on n variables and of degree d, we call a subset a blender if it is a closed convex cone invariant as a set under a particular action, which is the action of linear change of coordinates. Okay, so here are some examples. We have the blender of positive forms, which means that for every t and w, the image is always positive. We have the blender of convex positive forms, and finally we have this blender called Q, which is in fact the smallest blender, in the sense that every other blender always contains this one. It is always in the inside of any other blender. It is always contained there, and it is described by this. It is the forms which can be written as the sum of fourth powers of linear forms. Okay, so for example, in general, Q is always contained in K, and K is always contained in P. P is actually the biggest blender. But there's a theorem, an important result, that in the particular case of binary quartics, so two variables degree 4, Q and K are the same blender. They are the same set. They coincide. And we'll use this throughout the proof. Okay? So now we have the set. We have the important set to classify the relative position of two conics. That's exactly what we mean when we say that two conics are convexly nested. Two conics are convexly nested if the polynomial produced by phi gives us a polynomial inside this blender, or this blender, which are the same in fact. That is, the function the polynomial produced is positive and also convex. You see, if the polynomial is positive, then it has no roots, and this corresponds to the fact that the two conics do not intersect, they are disjointed. On top of that, they can also be convex or not. And what we're going to show is that the osculating conics of any curve with no sextatic point is always inside this blender right here. It is, so you have this stronger condition. All right, so let's start talking about the osculating conics themselves. Okay, so how do we find out the osculating conic at a given point of the curve? Well, by definition, the osculating conic is the only conic which has a contact of order at least 5 with the curve at that point. Analytically, this means that these five equations here are true. So the function produced by composing gamma with the implicit function of u should have a 0 at this point, which corresponds to the intersection of the conic with the curve gamma. But on top of that, we have that the first, the second, up to the fourth order derivative should also vanish at that point. So these 5 equations correspond to the 5-order contact, and it could be even higher. But the crucial remark is that all these equations are linear with respect to the coefficients of the conic. And since they are linearly independent, there's only a one-dimensional vector subspace of solutions. And this is exactly what we expected, because, as we talked before, a line through the origin corresponds to a single curve, a single conic of the projective plane. So in this way, we have a unique solution, right? Even though if we work in this line bundle, we have still to choose which multiple of the equation we are going to take. Well, by fixing one of the coefficients, say a equals to 1, if we introduce this condition, then we really have a unique solution, a unique implicit equation for the osculating conic. And if we do this for every value of s, we have a path of osculating conics in this space of conics in omega. However, as we stated, if we consider a smooth function lambda, which never vanishes, and we take the curve lambda times gamma, if we multiply by a scalar, then we'll have a new path of osculating conics, which still describes exactly the same osculating conics at each point, but with a different implicit equation. And by taking a suitable function lambda, we'll manage to find a particular way to parameterize this path of osculating conics with a really important property, which is that the tangent vector of this path corresponds to the double tangent line, the double line which is tangent to gamma at gamma of s. So we have a path in the space of conics, the tangent vector, which is an element of the tangent space. Since we are in a vector space, we can identify it with the space itself, so we can say that this direction corresponds to a conic. And it is not necessarily irreducible. In fact, we really want it to be reducible. It will be easier to prove what we want if this tangent vector is exactly this particular conic, the double tangent line. And we'll show that we can do that. So here's a very important lemma, which says that if for every s, value of s, the conic given implicitly by big gamma of s has a contact of order at least 5 with the curve, which is the case for the osculating conics, then the derivative of this path has a contact of order at least 4 with gamma at the point gamma of s. The proof of this lemma is just an exercise of differential calculus with those 5 equations we had, but once we have this, what can we do? Well, the derivative of lambda times gamma is given by this, and if we look at this expression, at this point we do not know the values of lambda or lambda prime. We should just see this as a combination of 2 implicit equations of conics, which is exactly what describes a pencil of conics. So a line in the space of conics, and in this case it has a really particular property, because since gamma has a contact of order 5 with the curve, and gamma prime, thanks to the lemma, has a contact of order 4, then every conic in this pencil must have a contact of order 4 with the curve little gamma at that point. It is precisely the pencil of conics with this property. That is, provided that gamma prime is not a multiple of gamma itself, because if these 2 conics right here represent the same curve, the same conic on the projective plane, then we don't have a pencil, we have just a constant, just a fixed curve. Well, and what is the condition? Well, for this not to happen, is the following proposition. The conics given by gamma and gamma prime are the same if and only if that point, gamma of S, is a sextetic point, which is why we must avoid them. From now on, we'll suppose that gamma has no sextetic point, and thus gamma prime, the tangent direction of any path of oscillating curves we've picked so far, is not the same. They do not correspond to the same conic, and thus we really have here the pencil we are looking for, as in this picture. So here's just to illustrate. I picked first the circle right here and the tangent line at this point, the double tangent line in fact, and I made that combination to draw this pencil. So every conic in this drawing has a contact of all the four at this point. Right, so now we can find the function lambda we're looking for. As you know, a conic given implicitly by an expression of this form, we can tell if this conic is reducible or not by checking this determinant. It vanishes if and only if the conic is reducible. So we should consider the following differential equation. The determinant of this matrix of a conic in this pencil should be 0. We are looking for the lambdas, the function lambda, that for every value of S, this happens. So it means that the derivative of the path we are considering, lambda times gamma, the tangent of this path is always the double tangent line. And it has a unique solution if we add a initial condition, say lambda of 0 equals to 1. Alright, so now we already have a path of conics parameterized in a very special way with that property that we just explained, and now we're going to use it to prove the result. So we'll start comparing osculating conics. In order to reach the theorem, we must compare two osculating conics, which means we should analyze the polynomial produced by phi if we compare gamma at a point S0 and the starting oscillating conic gamma of 0. But instead of taking just the endpoint, the extremity, which is what really is important, what we can do is take the whole path of polynomials. Now it's not in the space of conics, but actually in the space of forms of binary quartics, which we can produce by making S vary from 0 to S0. We consider the whole path in that vector space. We know that it starts at the origin, and what we want to show is that the other extremity lies within the cone, the blender, K24. And it turns out to be easier, to be simpler, to study the tangent vector of this curve. So we're going to take the derivative of the curve of polynomials produced by the oscillating conics. And the derivative is given just by that. Right, the path is somewhere. Here is just a representation. You know, this space of binary quartics is of dimension 5, so we cannot draw it. But the idea is the following. We have this path, and we want to know where it ends. Does it end inside the blender or outside of it? Well, the expression, as I said, of the tangent vector of this path is given by that. And in order to understand the quartic that it represents, the tangent vector, what we have to do is to insert the polynomial parameterization of the initial conic, which we already have. So we only ever need the polynomial parameterization of the first conic. This is really practical. And then we should input that in the implicit equation of the tangent line. We picked gamma, we chose a way to parameterize gamma after taking that function lambda, such that this is really simple. This is just the implicit equation of the tangent line, of the double tangent line at that point, at the point of contact. Right. In other words, the fundamental question is, does the oscillating conic, the first one, gamma 0, intersect the tangent line to gamma in gamma of S? Because if they intersect, then this would have a 0, right? Well, let's start by analyzing the tangent vector at the origin. So at S equals to 0. In this case, we're taking the first conic, and we're taking the very tangent line to the same conic, because we're evaluating at 0. So we know that this conic and the double tangent line must have an intersection, must have a tangent point, and since it is a double line, in fact, we have a fourth root, a root of order 4, which means that the polynomial produced by phi must be of this nature. It must be a fourth power of a linear form. It has a root of order 4, right? And in fact, a form of this type, when it's not a sum of different fourth powers of linear forms, just one such form, it belongs to the boundary of this cone, of this blender. That's something we can show. It's in fact even more than that. It's an extremal value of this cone. Well, in any case, this is important because it allows us to write the first term of the Taylor series of the curve phi of gamma s, gamma 0. So the first derivative, well, at 0 it is 0, so there's no first term here. And then we have the first derivative with respect to s times s plus higher order terms. Now, if we consider any other point on this initial conic, gamma 0, given by coordinates t0, w0, to find out whether this point belongs to another osculating conics, what do we have to do? We just have to evaluate phi at that particular point. But if we take a point which is not the first one, the point of contact at the beginning, then we know by this expression above that for a sufficiently small s, this expression is positive, which means that there is no intersection of the first oscillating conic with a sufficiently close oscillating conic, right? And in fact, a similar argument with further derivatives shows that there is also no intersection at that particular point of contact as long as we avoid sestectic points. So up to this point, we've proved that locally the osculating conics are disjoint. It is the weaker form of the theorem because since they are disjoint, they have no intersection, and since they evolve continuously, they must be nested. If you move just a little bit continuously, the only way that you cannot intersect two conics is if one is inside of the other. We cannot find completely disjointed like this by just moving a little bit, right? So locally, the oscillating conics are disjoint and nested. Well, on top of that, this property is transitive because if you have two conics, the first one contains the second, and then if you have a third conic such that the second one contains the third, then the first one will contain the third, right? And thus, this property will extend up until we pass through a sestectic point. Now, there's just one last thing to do, is to show that they are convexly nested. So, how do we do that? So far, we have studied the tangent vector at the origin, and that was enough to prove that the oscillating conics are disjoint and nested. But now we're going to have to look at the tangent vector at other points, so at s equals to s0. The quartic form that it represents is obtained by inserting, once again, the polynomial parametrization of the first conic, rho of gamma 0, into the implicit equation of the double line of gamma s0, of the next oscillating conic that we pick, which is given by the derivative gamma prime of s0. And from the previous result, we can assume that the conic gamma 0 is entirely contained in the conic gamma s0 as long as we change the direction in which we traverse the arc gamma, right? So we'll suppose that the oscillating conics are getting larger and larger and larger. Since the first conic is entirely contained in the following, if we take the polynomial parametrization, it will never intersect the tangent line because the tangent line to this bigger conic never enters the inside of this conic. Okay, and this already shows that the tangent vector of this path is a positive polynomial, is a positive quartic. But we want to show more. We want to show that it is convex as well, which is what we need. And for that, we have just another lemma, last lemma, which is just a result of real analysis. If we have a real, non-negative, and convex function, f, and another function g, which is non-decreasing and convex, then the composite is also convex. So let's apply this to our problem. We have the following function to analyze. We have the polynomial parametrization evaluated in the implicit equation of this double tangent line. Well, since it is a double tangent line, then it is given by an expression of this nature, right? Some linear form in the three variables squared. And here the polynomial parametrization, we have the coordinates x, y, and z as well. And so if we compose them, we just have this expression, okay? But since, as I said, the polynomial parameterization never meets the line, we know that this which is inside the square must be a positive quadratic function, polynomial, right? Which means that it is always convex. So this takes the role of the function f of the lemma, and then taking the square is the function g, and so the composite of those is also convex, which proves that the tangent vector of the path of polynomials that analyze the relative position of conics, the tangent vector of this path is always convex. It is always a positive convex form. So finally, we have a last step to talk about extremity. We just take the integral of these tangent vectors to find out where it lies. So since a linear combination with positive coefficients of a non-negative and convex function is still a non-negative convex function, this property extends to the integrals, and therefore, since for every value of s this is a convex form, a positive convex form, then the resulting integral, this polynomial right here, must also be positive and convex, so it lies within K, which is exactly what we wish to prove for our theorem. Voila, this is the last image. It's just the path, the real path that we have. The tangent vector is always inside the cone. It begins tangent, it begins at the border of the cone, but then it gets into the interior, and we will end necessarily inside this cone. So thank you very much.